All right, my friends, so I'm here to tell you about part 2 of the fundamental theorem of calculus. Okay, so what this says on a qualitative level is that if you take the derivative of the integral, basically they cancel and you get back to the original function. Derivatives and integrals basically are opposites. And we've talked about this before. And one thing basically that's going on here is if you take the derivative, so let's assume that b is some constant. If you take the derivative of the integral from b to x of f of t dt, then what this problem is saying is that the derivative and the integral cancel and you just end up getting f of x. So this is the second part of the fundamental theorem. You might be confused by the f of t in here. T is what's called a dummy variable. And what that means is that when you integrate and you plug in the bounds, the top bound minus the bottom bound, the t goes away, right? It turns into an x. So you may be wondering, like, why does this happen? Like, why does this work? Well, let's start with the inside, right? So this is saying that the derivative and the integral cancel, but you might wonder why. Well, let's see if we can prove this. So the integral from b to x of f of t dt. All right, so that's just equal to the antiderivative of f going from b to x. So that's just equal to the antiderivative at x minus the antiderivative at b. Now, then what they're asking us to do is to take the derivative of this. So let's take the derivative. Let's take the derivative of that. All right, so when I take the derivative of the antiderivative, that gets us back to our original function. That's what an antiderivative is. But then this f of b, this is a constant, right? It's just some random number. When you plug in a constant, you just get another constant, right? You get 12 or 20 or 3, who knows? But the idea is when you take the derivative, you get 0. So you get back to your original function. That's why you're able to do this. And that's why you're able to cancel the derivative and the integral. Okay, so this is kind of a proof of why that happens. Now, keeping that in mind, let's look at some example problems. And some of these you'll see are going to be pretty straightforward. Because again, what happens here is you take the derivative of the integral, you get the derivative of the antiderivative, that's the original. Okay, so let's take, for example, the derivative of integral 2 to x of t to the 5th dt. Now, when you see a problem like this, there are two things that happen. The derivative and the integral are going to cancel, and then you just plug in the x. So the derivative and integral cancel, and that x goes in. You're just going to get x to the 5th. And that's all you're going to do on these problems. Another place you'll see them, they might say, for instance, the f of x equals integral 3 to x of b squared plus 2 over e to the b db. Now, and then I'm going to ask you to find f prime of x. Okay, so f prime of x is going to be the derivative of f of x. So we're going to take the derivative of the integral 3 to x of b squared plus 2 over e to the b db. Now I'm going to use these same two steps. When I take the derivative and the integral, those cancel. I just take that x and I plug it in. So I'm just going to end up getting x squared plus 2 over e to the x. One thing I want to point out that you may have noticed or been curious about, this 3 doesn't matter. Because what happens is when you take the derivative of that part, it just went away, right? That's what we saw here. It was just some constant once we evaluated the integral, so it just went away when you took the derivative. So that's why that lower bound doesn't matter. You're just plugging in the x. Okay, so now another question you might be having is this. What if we don't just have an x in the exponent? So what if we have, say, the derivative with respect to x of integral 1 to the x cubed of cosine of t squared dt. Okay, now let's talk about what's happening. And again, I want to start with this integral right here. I don't know what the antiderivative of cosine of t squared is. Well, I do know. It's impossible to compute, so joke's on you. Okay, but let's just say it's some big F. Let's call big F an antiderivative and see if we can use that to show us what's going to happen. So this is big F of t going from 1 to x cubed. So what that's going to do, that's going to give us big F of x cubed minus big F of 1. Okay, well now what's going to happen? And again, I'm just trying to show you what's happening so we can come up with a rule. What's going to happen here when we take a derivative of this? So when I take a derivative of big F, I'm going to get back to let's go with big F prime. So big F prime of x cubed. But then by the chain rule, I have to multiply by the derivative of x cubed, 3x squared. And of course, the f1's a constant, so that just goes to 0. Okay, now, big F is the antiderivative, so this is just a regular f of x cubed times 3x squared. Okay, so let's look at what this is doing. Basically, the derivative and the integral cancel. And we're going to plug in the x cubed. And then we're going to do the chain rule on the x cubed. And I think it's important that we're just doing the chain rule on the x cubed, not on the whole thing. We're taking the derivative with respect to x. So we only do the chain rule on the part with respect to x. And hopefully that might help explain why you're doing it on that and not the entire thing. Okay, so the derivative and the integral cancel. So I get cosine of x cubed squared times the derivative of that x cubed, so times the 3x squared. So I could also write this as 3x squared times the cosine of x to the 6th power. So that's where that comes from. And these are the 3 steps you want to do. The derivative and the integral cancel. You plug in that upper bound, and you do the chain rule only on that upper bound. Not on the entire thing, just the upper bound of the integral. Let's do 1 or 2 more. So suppose we have to take the derivative with respect to y of integral 3 to the cosine of y of, I don't know, e to the t cubed. Now again, feel free to take a minute and pause this video, try it on your own. Okay, so the derivative and the integral cancel. That's good. Derivative and integral are opposite. And then we're going to plug in the cosine y, and then we'll do the chain rule. So cosine y gets plugged in there. So it's going to be e to the cosine of y cubed, and then we multiply by the derivative of cosine y, which is negative sine y. Okay, and there's our answer. So we got negative sine y times e to the cosine of y cubed. Okay, so that's how this works. And these are the steps you want to remember, right? The derivative and the integral cancel, you plug in that upper bound, you chain rule that upper bound. And that's going to happen on all these problems. One more type of thing, and we're not going to finish this necessarily, but maybe. If I asked you to take the derivative here of integral x to the 5th to 4 of cosine of t dt. Now, you might look at this and think, gee, Boris, my goose is cooked. I don't know what to do if I have an x to the 5th on the bottom. Well, hey, do we have a way that we can get the x to the 5th on top? Yeah. What we might remember is if we switch the bounds, it changes the sign. So I can switch this integral to be not x to the 5th to 4, but 4 to x to the 5th of cosine of t dt, and just put a negative in front, and then take the derivative of that. So when I do that, now the negative just chills, and then we just, okay, derivative and integral cancel, we plug in the x to the 5th, and then we multiply by the chain rule of x to the 5th. Okay, so that's part 2 of the fundamental theorem. Bring me some questions to class if you got them. This will show up occasionally, but it's some good stuff. I'll see you guys soon in the next video.